In the preceding 3 subsections, we have prepared all the building blocks that we need to construct the simplex method, and we'll join them together now and illustrate this with examples. We will assume that we begin with a basic feasible solution, so that we start with this tableau that is in canonical form. In some cases, it is easy to obtain such a basic feasible solution, but for some other problems this might prove to be more difficult. We will deal with this later in the course, and this will lead to artificial problems, artificial variables, and so-called two-stage simplex problems. We will see next that in addition to the tableau presented before, and this tableau in canonical form, we have to append a row at the bottom that takes into account the costs, and this will produce a row with the relative cost coefficients. And we will see that at the bottom right we will see the opposite of the current cost. Well, this tableau with this row at the bottom is the simplex tableau. We have now to introduce the cost in our tableau so that it becomes the simplex tableau. The cost is C transpose X, or C1x1 plus C2x2 up to Cnxn. So you can rewrite it as follows, and then what we can do is add it as a additional constraint in our tableau. So this means that we have to add a new variable minus z, right? So this means that we have to add a new column, right? And in this column, well, they will all be 0 because the other constraints do not depend on minus z, and the last element will be 1, right? And then we'll have a simplex tableau that is not in canonical form, because below the pivots we have these C1, C2 up to Cn, and what we can do is use standard pivot operations to bring zeros below the pivots, right? And this will lead this simplex tableau with associated costs in canonical form, and the last equation will then become like this one, but this is best illustrated by looking at the tableau itself. Well, this is best explained by looking at tableaus. We have here the previous tableau from the previous explanation in canonical form, and we have added here a new virtual constraint that takes into account the cost. And to do this, we had to add this column over here with this new variable minus z, right? And in this column you will always have zeros, and at the bottom a 1. So even if you do row operations, it will look the same. So usually what is done is that this column is not shown, right? You have to imagine it, and that it looks like this. So if you look at this new tableau, which we call now a simplex, well, it is not in the canonical form, because we have here the basic variables and we do not have zeros below the pivots that are over here, right? So we have to create zeros below the pivots, and you should not forget to do this, because this is how we'll have the reduced costs appear, and this is how you can decide which column, right, which variable should enter the base. We will illustrate this later, right? So how can you create zeros below the pivots? Well, you have to do row operations. Very simple. This row minus C1 times this row will also have to subtract C2 times the second row, and so on, right? And if we do this, we can see that we create zeros over here, and here we obtain the reduced costs. How does this reduced cost appear? Well, let's just see what happens. So we'll have CM, we'll do this for this column, and then you'll see that you'll have something similar for the other column. So we'll have CM plus 1 minus C1 times this one minus C2 times this one, and then we'll continue up to CM times this one, right? And if you remember, this is the definition of ZM plus 1. So indeed, this is the reduced cost or the relative cost associated with the non-basic variable xm plus 1, right? And what is interesting is that over here what appears is, well, 0 minus C1 times this one minus C2 times this one to 0 up to minus CM ym 0, and this is indeed equal to minus, so the opposite of the cost that you have for this simplex tableau. So from this simplex tableau that is now in canonical form, you can continue to work on. Well, when you have arrived at the canonical simplex tableau, you have the so-called relative cost coefficients or reduced cost coefficients, and they tell you if the cost, the objective function, will increase or decrease if you let the associated variable xj join the base. Well, when all those relative cost coefficients over here, these ones associated to non-basic variables, are non-negative, well, then the solution is optimal, because there is no non-basic variable that you can bring in the base while at the same time decreasing the cost. If you bring a non-basic variable in the base, well, the cost will increase. So you have the optimal solution that you can read from the simplex tableau. x1 is y10, x2 is y20, and so on. Well, if some of the relative cost coefficients are negative, it means that if you bring the corresponding variable in the base, well, the cost can be decreased, and this brings an improvement. If more than one of the RJs is negative, well, it is common practice to select the most negative value, so the variable that is associated to the most negative relative cost coefficient. Well, it could happen that two variables have a relative cost coefficient that corresponds to this most negative value, and then usually what is done is to select the variable most to the left in the tableau. Well, we can now introduce the simplex algorithm. You have to form a tableau with the corresponding basic feasible solution. In some cases, as we will see, this will be rather easy. In other cases, well, this might involve a so-called artificial problem, but this will be treated later. Make sure that the tableau is in canonical form so that you have zeros below the pivots, and if necessary, this will require elimination using row reduction. Well, once you have your simplex tableau in canonical form, you can look at the relative costs. If all of them are positive, well, then you have ended up with the current basic feasible solution being optimal and you are at the end of the algorithm. If this is not the case, that means that there is at least one relative cost that is negative. Well, this is step 3, right? You choose the one that corresponds to the most negative relative costs, and the associated variable xq can join the base. So you have your bases here, and here you have the basic variables, here you have the non-basic variables, and by choosing the most negative relative cost, you have selected xq. This is the variable that will have the biggest impact on the cost, in the sense that it will reduce the cost and it will be the variable that will decrease it the most. So this variable can join the base. Of course, now we need a variable to leave the base, and we go to step 2, and for that we have to look at the ratios. You construct this ratio here, and you have to look for the smallest positive ratio of this type. If all those ratios are negative, well, then you have an unbounded problem. But this is not likely, because it would mean that your original problem is not well posed, right? So in general, you can select among those ratios the smallest positive ratio, and this will amount to select an index p, and you will have now a variable xp that can leave the base, right? And since xq is joining the base and xp is leaving the base, you now know that the pivot is ypq, and then you use step 1, you use, well, elimination procedure, pivoting, to make sure that the new basic variable is now xq, and then of course you have to return to step 2. Well, let us come back to our diet problem, our diet of peanut butter and steak. So we need to determine x1 the number of pounds of peanut butter and x2 the number of steaks. Of course, this is a minimization problem because we want to minimize the associated costs. But at the same time, we have to make sure that our supply of proteins is high enough. We need at least 4 units of protein per day, and we have to make sure that the number of proteins that we get from our diet, which is this quantity, is higher than the daily supply that you need. And of course, x1 and x2 are positive. This is our optimal diet linear programming problem. Well, of course, this problem is not in the standard form because we have here an inequality larger or equal, right? Well, to bring this in the standard form, we have to work with variables that are positive or 0, and to transform this in an equality constraint, we'll have to subtract something positive. So this one will become x1 plus 2x2 minus x3 is equal to 4, and what we'll have to add is x3 positive or 0. If you subtract something positive over here, you can ensure an equality constraint, and this is what we do over here. So we start from the problem in standard form. We have the two operational variables x1 and x2, and x3 is a surplus variable that results from transforming the original problem into one that is in the standard form. Well, we have to write this problem in the standard form, in the form of a tableau, and this is the initial tableau that we get. So here we can see the single constraint, and here below we have written the cost, as you can see over here. Here we choose to make the variable x1 a basic variable, so this is here then the pivot, but we could also have made x2 the basic variable, right, and divide the equation by 2. And the problem is with this second case is that we would have ended up in the optimal solution directly, and since this is meant to explain, well, the simplex methods, we have chosen as a basic variable x1 so that we can kind of see what happens if you use the simplex method. But anyway, since we have chosen x1 to be basic, this is the pivot, and you can see that this tableau is not yet in canonical form, because if this is the pivot, we need to have a 0 below the pivot. So to initiate the simplex procedure, we have to do this row operation to create a 0 over here. So as said before, we bring the tableau in its canonical form by having zeros below and above the pivots. Do not forget this when you do exercises. So this is a trivial row operation. It's the second row minus 2 times the first row, and you then end up with the second tableau, and this tableau is in canonical form. You can read the initial basic feasible solution, right? This is a basic variable, and these are two non-basic variables. This is a operational variable, and this is a surplus variable. So as you can see, this one is basic, so you can read the initial feasible basic solution from the tableau. So we have x1 is equal to 4, and you've set, of course, the other two variables x2 and x3 to 0. And as you can see, since we read here the opposite of the cost, that the associated cost is $8. So it's 4 times $2, right? And you can see here that R2 is constructed from, well, it's 3, and this is really C2, and then we subtract 2 times 2, and in this case this is the Z2 that we had in the previous slide. In some of the slides that I have skipped, there is an interpretation of this Z2, so you can have a look if you're interested, but you can see that this reduced or relative cost is -1 in this case. And this means that, well, it will be interesting to bring the variable x2 into the base to replace the variable x1, because it will decrease the cost. So this is our second tableau. Here we have the initial feasible solution. We see that the associated cost is indeed 8, because this is the opposite of the cost, and indeed the reduced or relative cost is R2 here. The interpretation is that the costs will be decreased by 1, in this case dollar, per stake that we bring into the solution. Let us illustrate this. We have, of course, a constraint, and this constraint is 1, and this 1 is A11 from the original problem, times x1 plus 2 times x2 this is a12 minus x3. This is to bring everything to an equality. So x3 is a surplus variable, is equal to 4. And we can see indeed that our initial feasible basic solution meets the constraint, because we have, well, 1 times 4 plus 2 times 0 minus 0 is equal to 4. So we want now to take x2 is equal to 1 and to see what will happen, but of course we have to make sure that the constraint is still met. If we take x2 is equal to 1, we'll have to adapt x1. So we'll have here plus 2 times 1, right, because we take now x2 is equal to 1. Here we'll still have minus 0 is equal to 4, and this means that we have to take x1 is equal to 2 to meet the constraint. So we'll have here 1 times 2, and so indeed we see that if we take 1 unit of x2, so x2 is the number of stakes, so 1 stake, we have to adapt x1, and x1 will be equal to 2, right? And so now we can compute the associated cost, and the associated cost is given over here. It's c1 x1 plus c2 x2. So in this case c1 is 2, so the cost associated to x1 is 4, and c2 is equal to 3. We only have 1 unit of x2, so this will yield 3. So indeed we have 7 here, and you can see that the cost has been reduced by $1 by bringing in 1 unit of x2. Well, with this second tableau we had identified that R2, the reduced cost, was negative, so it makes sense that x2 joins the basis, and of course x1 will have to leave the base. So we have to make a 0 or create a 0 below the pivot, and to make sure that this pivot is equal to 1, right? So we'll have to do this elementary row operation to create a 0 over here and multiply the first line by a half, and we then obtain the following final tableau. We have the pivot over here, so we can read the value of x2. x2 is equal to 2. The other variables x1 and x3 are non-basic, so they are 0. x1 is an operational variable, and x3 is the surplus variable that we had introduced to transform the original problem into one that is in the standard form. And you can see here that this is the opposite of the cost, so the optimal cost is $6. Well, we can have a look at the interpretation of the surplus variable x3 is equal to 0. Remember that originally we had a constraint x1 plus 2x2 is smaller or equal to 4, and we had transformed this into an equality constraint where you had minus x3 is equal to 4, and of course the variables x1, x2 and x3 were all positive. So here you see that x3 is equal to 0. So this means that in the initial inequality constraint we have indeed equality over here. So when the surplus variable, it will also be the case if it is a slack variable, is 0, it means that the corresponding inequation in the original constraints is met with equality. So in this final tableau we can again have a look at the interpretation of R1. R1 is associated to x1, which is an operational variable. So R1 is called a reduced or a relative cost. And in this case, R1 is equal to a half. So this means that if you increase X1 by 1 unit, well, the cost, and of course you take into account the constraints, we'll have to adapt X2, well, the cost will increase by a half, right? So remember that the initial constraint after transformation to the standard problem has become X1 plus 2x2 minus x3 is equal to 4. You will see that, well, the optimal solution meets this, well, constraint. If you now increase x1 to 1, right, and you leave x3 is equal to 0 because you want to meet the constraint, well, then you'll have to take x2 is equal to 3 over 2. This is what we have over here, and then you can compute the associated costs. And if you do this, knowing that C1 is equal to 2 and that C2 is equal to 3, you will see that it is, well, 13 over 2, which is equal to 6.5, right? And you can see that the cost increases indeed by $0.50, right? So as you can see, this is indeed the correct interpretation of R1. Well, in this final tableau, we can also have a look at R3, the reduced cost associated to the surplus variable x3. And since x3 is not an operational variable, we will call R3 a shadow cost. And the interpretation is that the cost will increase by $3 over $2 per unit increase of the surplus variable x3. And the idea is that we replace the original constraint x1 plus 2x2 larger or equal to 4, and in standard form x1 plus 2x2 minus x3 is equal to 4, by this one over here. So we increase 4 to 5. Indeed, this is what we see here. If we have a unit increase of the surplus variable x3 and you have a 1 over here, well, when we have here an equality, x1 plus 2x2 is equal to 5. And if you look at the optimal solution with this inequality constraint where 4 is replaced by 5, you will see that the optimal solution will change from x1 is equal to 0, x2 is equal to 2, you can read it from this tableau, and x3 is equal to 0, to this optimal solution. So 2 is replaced by 5 over 2. If we look at the associated cost, right, it's C1 x1, x1 is equal to 0, plus C2 x2, right? Well, C2 is equal to 3. You can see here in the optimal solution that the value of x2 goes from 2 to 5 over 2, so there is an increase of a half. Since C2 is equal to 3, we'll have an increase of $3 over $2, and this is indeed what we see over here. Well, before we go any further, we'll return to this linear program that we had considered as an example and that we had already transformed in a standard form. So in this case, we have already written the initial tableau. So the 3 constraints here can be found over here, right? And this is the part that comes from the cost, as you can see, right? In this case, since our original problem only involves inequalities smaller or equal, then we had here, well, slack variables, and you can kind of see that we have our problem already in canonical form, right? And it's easy to find an initial feasible basic solution, right? Here we see that the basic variables are the three, well, slack variables, and the non-basic variables are the operational variables x1 and x2. And you can see that the basic solution here is, of course, x3 is equal to 12, x4 is equal to 10, x5 is equal to 8, and you set the non-basic variables to 0, as you can see over here, right? So in this case we have zeros below and above the pivots that you see over here. So this means that the coefficients that you see over here associated to the non-basic variables are the reduced cost. So this is R1 and this is R2, right? So to select the variable that will enter the basis, we take the most negative one, and it will be this one over here, right? So x1 will enter the base, but now we have to kind of find which variable is going to leave the base, and for that we have to write this column, which is this one over here. So let's write it. It's yi0 divided by yi1, because the variable x1 is going to enter the base. So 12 divided by 3 is 4. This one over here, 10 divided by the corresponding element in the first column, 3. So we have 10 thirds, right? And here we have 8 divided by 4. So we have 2. They are all non-negative, and we have to take the smallest one, and in this case it's this one, right? So the pivot is over here, right? And we know now that, well, x1 is entering the base and x5 will be leaving the base, right? So what we need to do is create zeros above and below the pivot. So we'll have to do elementary operations, right? Here the multiplier will be the element to eliminate divide by the pivot, and you'll have something similar over here, and it will be 3/4 as well. And we need to create a zero below. So since we have a minus here, element to eliminate divide by pivot, so we have -1, right? So we are now ready to do the elimination procedure. In this initial tableau, what we have to do as well is to multiply this third line by a quarter, so that we have here in the second tableau a unit pivot, right? So I will leave the calculations to you, the details, but if you do these calculations, well, you end up with this second tableau, and we have non-basic variables x2 and x5, and basic variables x1, x3, and x4 that you can recognize, because that's where you have the pivots and you have zeros below and above the pivots. The basic solution is simply obtained by setting the non-basic variables to 0. And if you do so, you can read the solution. For example, for x1, you take the first column, right? And you have x1 is equal to 2. Third column, x3 is equal to 6, and fourth column, x4 is equal to 4, right? And this is indeed what you obtain here. So you should always check, of course, if the new basic solution meets the constraints. Well, you should check, of course, that it remains feasible. If not, you have made a mistake, and it should also meet the specification. If it doesn't, you have made a mistake and it doesn't make sense to go any further. So for instance, here x2 is equal to 0. So in the first constraint we have 3 times x1 plus x3, and we see indeed that this is equal to 12. So the first constraint is met, and you should of course check that for the other constraints, and you should always check that in every tableau at every step. So now we can continue. The reduced cost R2 is still negative, so this basic solution that we have found is not yet optimal, but we know now that x2 is going to enter the base, and we need to decide which variable is going to leave, right? So we need to compute this ratio yi0 divided by yi2. So in this case it's 6 divided by 5 over 2, so that's 12 over 5. It's 4 divided by 3 over 2, so that's 8/3, and it's 2 divided by a half, so that's a 4 over here. So obviously the smallest positive element here is this one over here, and it corresponds to I is equal to 1. So you can see here that, well, since this one is going to become the new pivot, well, x3 is going to leave the base, right? So this is the new pivot, so we have to kind of write the new row operation to create zeros below the pivot. So the element to eliminate divide by the pivot, so that's 3 over 5. The element to eliminate divided by the pivot, so that's 1 over 5, and then we need to create a 0 below the pivot in the last line. The element to eliminate divided by the pivot, so that's minus 2 over 5, and then of course we need to multiply the first row by the inverse of the pivot, so that's 2 over 5, right? And now you should do these elementary row operations. Well, this is how you obtain the third tableau, and as you can see there are two non-basic variables, x3 and x5, and the basic variables are located where you have the pivots, so they correspond to x1, x2 and x4, right? So we have the following basic solution. You set the non-basic variables to 0, and you can read from the tableau that, well, x1 is going to be 4/5, x2 is 12/5, and x4 is 2/5, right? And this is indicated over here. Again, you should plug in this in the original constraints to see if this meets the specifications, and these specifications are over here. I'll leave this to you as an exercise. As you can see here, we have the reduced costs are 3, which is positive, and the reduced cost are 5, which is positive as well. They correspond to the, well, non-basic variables R3 and R5, and this means that we have ended up at the optimal solution. So we can read the optimal costs. Well, our problem is a minimization problem, so you have to take this one and take the opposite value, but the original problem was a maximization problem, so the original maximization problem has a cost of 52 over 5, and the minimization cost is minus 52 over 5. So you can see here that, well, the non-basic variables x3 and x5 are equal to 0. This means that in these equations here, the slack variables x3 and x5 are 0. So this means that we use all the cutting time and all the washing time. But you can see here that x4 is equal to 2/5. So here we have some slack, right? So this means that the sorting time has not been used at its maximum, right? So we also can have a look at R3 and R5. I'll take the largest one, and since they are associated with slack variables, we call this R3 and R5 shadow costs, and the interpretation is as follows. If you take x5 in this case is equal to 1, well, this will lead to a decrease in the washing hours to 7 hours. How can you see this? Well, here you have the original constraints, right, with inequalities, and here you have the constraints in the standard form. So if you set x5 to 1, well, this is equivalent to saying that this is at most 7 hours, right? And the interpretation is that, well, if you set x5 to 1, the minimization cost, which is minus 52 over 5, so this is minus 10.4, will be increasing by 0.7, so we'll have minus 9.7. So this means that the maximization cost will go to 9.7, right? Do not forget that we have to multiply by 100, so this corresponds to 970 euro. By the way, I didn't write it, but the original maximization problem had an optimal cost of 10.4 multiplied by 100, so this corresponds to 1040 euro, right? So you can see that if, well, we take x5 is equal to 1, so this is a decrease in the number of washing hours, well, the maximization cost, so the profit decreases. Whereas if, of course, we take x5 is equal to minus 1, and this would be an increase in the number of washing hours, well, the minimization problem would have a cost that will decrease by 0.7, right? And the maximization problem would then be 11.1, and this corresponds to 1,110 euro. So you can see that in this case, if you have an hour that is available by looking at R3 and R5, well, it makes more sense to take this hour and to allocate it to washing, because you see that if you have 1 hour of washing more, right, you can increase the profit by 70 euro, right? Whereas if you would allocate this hour to the cutting, you would only have an increase of 2/5 times 100, so that's 40 euros. Well, we can check this in MATLAB using the command linprog. So here in front you have the objective function. We have transformed this to a minimization problem, and here you have the constraints. In MATLAB you can leave them as inequality constraints, smaller or equal than, and here you have the constraint on, well, the non-negative constraint on x1 and x2. We'll use the simplex algorithm and then you'll obtain the solution. And for the sensibility analysis, we'll verify that if we have 1 hour of washing more, well, this will lead to an increase of the cost in the original maximization problem. So let us run this, and this is what you obtain. We indeed obtain the good solution. So x1 is equal to 4/5, and well, x2 is equal to 12/5, and well, the solution of the minimization problem is minus 52/5, so that's minus 10.4. And if you look at the original maximization problem, we have indeed 10.4. And we see here that if we have more washing, the solution changes. And indeed, if you look at the cost of the original maximization problem, it has increased by 0.7. If we multiply this by 100, we have indeed a cost or a profit here that has increased by 70 euros. Well, let us do another exercise, one that is in the slides. It's a linear program. We have a maximization problem, and we have three, well, constraints of the type, well, smaller or equal than. So to transform this into the standard form, remember that this is necessary to be able to use the simplex method. We have to transform the maximization problem in a minimization problem. Simply take the objective function and multiply it by -1. And we have to transform these inequations in equality constraints. And this can easily be done here by using, in this case, slack variables x4, x5 and x6 that you have to constrain to be positive or 0, right? And in this case, it will be quite easy to find an initial basic feasible solution. This is the case every time where you have constraints of the type smaller or equal. If all of the constraints are of the type smaller or equal, well, you'll have a slack variable in each of the constraints, and by definition a slack variable will only appear in only its corresponding equation. So if you write this in the tableau, you always have, for instance, for x4, the fourth variable, 1 0 0, for x5 0 1 0, x6 0 0 1. So you can choose as basic variables x4, x5 and x6, right? So in this case, this, well, initial feasible basic solution is easy to find. It might not always be the case, as we'll see later. Well, this is the initial simplex tableau, and we obtain it by writing the three constraints, right? Here you have the three operational variables, and here we have the three slack variables, coming from the fact that we have transformed the problem in its standard form. In this case, this will be the basic variables, and these ones will be non-basic. And you can read the initial basic feasible solution from the tableau. So x4 is equal to 2, x5 is equal to 5, and x6 is equal to 6. x1, x2, x3 are non-basic, so they are set to 0. So what we'll do now is also write the costs in the tableau, and this is what you obtain. And as you can see, well, below and above the pivots we have zeros, right? This will be the new pivot, and we'll see how this one is selected. But so far the pivots are over here. We have zeros below and above. So these ones come from the cost, but they are also, since in this case these are operational variables, the reduced costs, right? And what we have to do is to select the one that it is the most negative. Well, we have -3 over here, -3 over here. We'll select this column, so we'll take the variable that is most to the left. So this is x1, so we know that x1 is going to join the base. So now we have to kind of determine which variable is going to leave the base. So we need to compute this column here. This has to do with this computation of the epsilon that we have seen previously, and this is coming from step 2. We take this value divided by this one, that's 1, this one divided by this one, that's 5, and this one divided by this one, so that's a 3. We take the smallest positive ratio, and this is this one over here. We had selected this column, now we have selected this row, so this explains why this is the new pivot, right? So we need to create zeros below the pivot, so we'll have to do these row operations. Well, we'll just do this one. We need to create a 0 over here, so we take the element to make 0 and we divide by the pivot, and this explains the multiplier, and we have a minus. So this means this row minus a half this row. And well, the two other elementary operations are given over here, and we'll have to multiply the first line by a half so that we obtain a pivot that is 1. If we do this, this is the second tableau, the new simplex tableau that is obtained. And as you can see here, we have now basic variables x1, x5 and x6. These ones are non-basic, right? And the new feasible basic solution can be read from the tableau. It's x1 is equal to 1, x5 is equal to 4, and x6 is equal to 4, and the non-basic variables x2, x3 and x4 are set to 0. So we can have a look again at the reduced cost. We see that there is one that is still negative, so this means that we can make sure that x3 is going to join the base, right? So now we have to look at which variable is going to leave the base, and again we'll have to compute this column, right? So it's the elements from the last column divided by the elements of the third column, since it is this column that is going to do the pivoting, right? So this one divided by a half, that's 2. This one divided by 5 over 2, that's 8 over 5. And 4 divided by 0, that's, well, tending to infinity. So the smallest value is this one over here. So we have selected this column and this row, so the pivot is 5 over 2, right? So again, we can create zeros above the pivot and zeros below the pivot. Here it's easy, we already have a 0, so we have to do these elementary operations, right? And then we have to multiply the second row by the inverse of the pivot, so that's 2 over 5. Well, every time you have a new simplex tableau, you should compute the new basic solution. So here it's x2 is equal to x3 is equal to x4 is equal to 0. We see that x1 is 1, that x5 is 4, and that x6 is 4 as well. And you should check if this new basic solution is indeed feasible. It's the case over here because all the elements are positive or 0, and you still have to see if this new basic feasible solution still meets the criteria of the original problem. If you plug these in, well, you still need to have this, well, equality constraints that are met in the standard form. Check this, because if you have made a mistake in the computation of the new simplex tableau, you will see this, and you might see that, well, your new basic feasible solution no longer meets the specifications. Well, in this second tableau we had seen that the reduced cost corresponding to x3 was still negative, right? And this says that x3 is going to join the basis, and we had isolated this element as the smallest positive element. So we can kind of see here that, well, x5 is going to leave the base. So this is the new pivot, and here are the associated elementary operations. If you do these elementary operations, you obtain this third simplex tableau, and you can see that it's also the last tableau. So the associated, well, basic feasible solution is optimal. Indeed, in this last row of the third simplex tableau, we see that our elements are positive, and this is where we have the reduced costs. We have to look at the non-basic variables, and as you can see, they are all positive. So this means that the solution is optimal, right? So it's easy to find the optimal solution. You set all the non-basic variables to 0, right? And then you can read the solution from the tableau. x1 is equal to 1 over 5, x3 is 8 over 5, and x6 is equal to 4, and this is what you see over here. For the minimization problem, the underlying cost is this one, and you have to put a minus sign in front, right? And if we look at the original problem, then we can forget about the slack variables, and the original problem was a maximization problem, so we have to take the opposite of this one, which is also the one that we have over here, right? So it's also interesting to see that the slack variables x4 and x5 are equal to 0, right? So which means that the two first inequalities are met with equality, and we have a slack of 4 in the last constraint. Indeed, with x1 is equal to 1 over 5, x2 is equal to 0, and x3 is equal to 8 over 5, we can see that if you plug this in, which is also a good idea to check your solution, that, well, we have 2 over 5 plus 8 over 5, that's 2, so this one is met with equality over here, right? If we plug the solution in the second equation, we have 1/5 with 24 over 5, so that's 25 over 5. So again, it's met with equality, right? So this is why the slack variables x4 and x5 are equal to 0. Whereas if you plug this in the last inequality over here, so you have 2 over 5 plus 8 over 5, that's 10 over 5, that's 2. And here you see that, well, you do not meet here the equation with equality. So you have this one here, so you have 2 that is smaller than 6, right? So indeed you have some slack, and this is why x6 was set to 4. Well, here we can again check using MATLAB. So this is the objective function that we had obtained when transforming the maximization problem into a minimization problem. In MATLAB you can still use inequality constraints as long as they are inequalities of the type small or equal, which is the case, so you do not need to go to the standard form. And here you have the non-negativity constraints on the 3 variables, and we'll use, well, the simplex method, and then we can run the code. And indeed we obtain x1 is 1 over 5, x2 is 0, x3 is 8 over 5, and the cost is minus 27 over 5. Let us do another exercise. The question is as follows. The owner of a shop is producing automobile trailers. He produces, well, flatbed trailers, economy trailers, luxury trailers, and he wants to find the best mix of his 3 products, knowing that his shop is limited to 24 days a month of metalworking and 60 days a month for woodworking. And then you have the production data per trailer type, right? Flatbed, economy, and luxury in terms of metal working days, wood working days, and profit. So for instance, a flatbed trailer needs half a day of metalworking, 1 day of woodworking, and generates a profit of $1,000 and will work in kilo dollars, right? So 6. Push the pause button and try to do this exercise by yourself. Well, the first thing that you have to do is to introduce variables, and we'll introduce the variables x1, x2, and x3 for the number of flatbed, economy, luxury trailers produced a month. And then you have to, well, write down the problem in a mathematical form first, right? So the idea is, of course, to maximize the profit. Well, you can read the profit from the last row, and it will be 6x1 plus 14x2 plus 13x3. This is what you see over here. You have, well, limitations in terms of the number of days allocated to metalworking and woodworking, respectively 24 and 60. So you should compute with this production x1, x2, and x3 what are the number of days allocated, for instance, to metalworking. And it will simply be a half times x1 plus 2 times x2 plus 1 times x3, right? So this is what you see over here, and this has to be limited by 24. So this gives you the following constraint, and you have something similar for woodworking days. So x1 plus 2x2 plus 4x3 is now limited to 60 days a month, and this yields this second constraint. Of course, the variables x1, x2, and x3 are non-negative. So now you have the mathematical problem. If you haven't done so, you should pause now and try to obtain the problem in its standard form. So here you have the problem under its standard form. Of course, the maximization problem is transformed into a minimization problem, so you have to take the original objective function and multiply it by -1. So in here you had two constraints of the type smaller or equal, so this means that you have to use slack variables. So you introduce a first slack variable x4 in the first equation to obtain an equality, and you obtain then a second constraint of the type equality by adding again a slack variable x5 now. So you have three operational variables, x1, x2 and x3, and two slack variables, and of course they are constrained to be larger or equal to 0, and this is the problem in its standard form. Well, this is the initial tableau. So in this case we have, well, m is equal to 2, there are two constraints, and n is equal to 5, so there are two basic variables, x4 and x5, and n minus m, so that's three non-basic variables, x1, x2 and x3, and you can read the solution from this initial tableau. You set the non-basic variables to 0, and then you can see that x4 is equal to 24 and x5 is equal to 60. Right? You can see here that we have the pivots, and we have indeed zeros above and below the pivots. You should always check this. So here we have the cost, but here we also have the reduced cost, so we can start the simplex procedure and determine the most negative R, and it's of course R2. Right, so this means that x2 will enter the base, right, and we need a variable to leave the base. So what we'll do is compute yi0 over yi2, right? So this one divided by this one, that's 12. This one divided by this one, that's 30. So this means that the smallest non-negative value in this column is 12, and we have here the new pivot. So we'll have to do row operations to create zeros below this new pivot. So we'll have this here. The multiplier is the element to eliminate divided by the pivot. So this is a 1 here, and the element to eliminate, that's minus 14 divided by 2, so we'll have minus 7, and of course we'll have to multiply the first line by a half. By the way, x2 is joining the base, but you can see from the first line that the variable x4 will be leaving the base. That's where you had the previous pivot in this line. Well, after calculations, elimination procedure, you obtain the second tableau, and you will see here that you have two basic variables, x2 and x5. This is where you see the pivots, and you have three non-basic variables, x1, x3 and x4, that you can set to 0, and x2 is equal to 12 and x5 is equal to 36, and this leads to the basic solution. At every step you should check that this basic solution still meets, well, the original constraints of the problem in the standard form, and you will see here that this is indeed the case. So we should look at the reduced costs and see if there is one that is negative, and here there are two. The most negative one is this one, so this will mean that x3 will join the base. So we'll write the column yi0 divided by yi3. So that's this one divided by this one, that's 24. Then this one divided by this one over here, that's 12, right? So we take the smallest non-negative value, that's this one, and this means that we have now isolated the pivot. So x3 will join the base and x5 will leave the base, right? So we have to create zeros above and below the new pivot. So we have to perform row operations. The element to eliminate divided by the pivot. So the multiplier will be 1/6. And here the element to eliminate is -6 divided by the pivot. So it's -2 over here. And of course what we'll have to do with this second line is multiply it by the inverse of the pivot to produce a 1. So after calculation you obtain this third tableau, and you can see again that there are of course two basic variables, and this time they are x2 and x3, and the other variables are non-basic. The basic solution is obtained by setting the non-basic variables to 0, and you can read the value of the basic variables from the tableau. So x2 is equal to 6 and x3 is equal to 12. So here's the basic solution, and you should check that it meets these constraints that you have in the standard form, and you can see that this is indeed the case, right? So we see here that we have this reduced cost R1 that is negative, so we have to let x1 enter the base, and now we need to kind of see which variable needs to leave the base. So this is why we are computing yi0 divided by yi1, right? So this one divided by this one, so we have 36, and this one here divided by this one, and this is 72. So obviously the smallest non-negative value is this one, so we can see here that the pivot will be this element over here. So x1 will enter the base and x2 will leave the base, right? So we have to create zeros below the pivot, and here we'll have to do the following elementary operation. So the element to eliminate is this one divided by the pivot, so 1 here for a multiplier, and over here the element to eliminate divided by the pivot, and this will produce a multiplier -9, and we'll have to multiply the first equation by 6 to produce a pivot that is 1. If you go through the calculations, you obtain the fourth and final tableau, because you can see over here that all the reduced costs and all the shadow costs are positive. So we have arrived at the optimal solution. If you set the non-basic variables to 0, this is what is done over here, you can read the solution for x1, it's 36, and for x3 it's 6, right? So this is the optimal solution. Of course, as usual, you should always check that it meets the constraints, right? You can read the optimal costs from this value. If you look at the original maximization problem, well, then it will be $294 but if you look at the minimization problem in the standard form, you'll have to take this one and multiply it by -1. You can also have a look at the R values associated to the slack variables, and these are called the shadow costs. So here the first shadow cost is R4 and the second one is R5, and we have seen previously that it can be seen as follows, and there is an interpretation that if you have an extra hour of metal working, it will generate here $11 extra in profit, whereas if you have an extra hour of wood working, it will only generate an extra profit of $0.5. So if you have an extra hour, of course it's obvious that you should allocate it to metal working. As usual, we check the result with MATLAB. This is the objective function. MATLAB assumes that we have a minimization problem, but it is possible to introduce constraints smaller or equal than and equality constraints. So you do not need to go to the standard form as far as the constraints are concerned, right? So these are the smaller or equal inequalities. These are the non-negativity constraints on the variables x1 to x3, and then you use the function leadproc. We do it 2 times. The second time we just add an extra hour of metal working just to see if this sensitivity analysis that we have done using the shadow costs is correct. Well, let us run this code and check the result, and indeed we see x1 is equal to 36 and x3 is equal to 6, x2 is set to 0. We have the same cost for our minimization problem, and we see that indeed if we have an extra hour of metal working, the solution changes, but the cost associated to the maximization problem, 305, increases by $11 with respect to the original problem that we have set. So we can see here that our sensitivity analysis is indeed correct. As you know, there is a PDF document available on the web page of the course with a lot of exercises that you can do by yourself. As usual, only the final solution is given.